Good afternoon, this is Schweitzer, and we're going to be doing a couple of little lab demonstrations here and going through some answers to a few pages that we normally would just do in class. So if you can't be at class, then we'll do our best here. So our first experiment is actually we're going to get started here, explain it at the bottom here, and then we'll let it sit for a while and then we'll come back to it. So at this point, we're looking to determine the specific heat of a block. That block is this block right here. Okay. And we weighed this block, and I weighed the block already, so let's put in some of this information. The general idea of this particular demonstration is that we are going to take a hot block, and the block is going to be 100 degrees Celsius. And I realize there's a video right there, so some of our table you can't see, but you'll see it eventually, or I'll move it up. So, and then we're going to take that thing and we're going to drop it into a known collector of water. That known collector is in the calorimeter. It even says calorimeter on it, but it's just an insulated cup, a little styrofoam inside, and the water that's in there is the collector. So really it kind of looks more like this. I'm trying to insulate, and it's got a cover, but so inside here we have 100 grams of water, and I'm going to try and move this up as much as possible so we can see it. I think we're getting close. There we go. So we have unknown water is 100 grams. Now, this case, the temperature initial, I don't know yet, I'll measure. You'll notice there's water boiling in the background here. This water is boiling for a purpose only other than to get my block to 100 degrees. And I'm going to carefully drop the block in here. And we're going to let this thing just heat at about 100 degrees. So the block's now absorbing energy to the point where it just about stopped boiling. So the block itself has a mass of 121 grams. Okay, and the temperature initial of the block is going to be 100 degrees Celsius when I take it out of there. So the water that you see in the beaker there really means nothing. I didn't measure the volume. That's not the 100 milliliters of water. It's actually right there. So we'll get this thing out of here for now because we don't need it yet. I'm going to drop my thermometer into the calorimeter water, which is right here. So this is now measuring the temperature of that water. We'll leave it sit there, I guess. It won't take long. The specific heat of the water is 4.18. I do know that when the block gets dropped into the water, it's going to radiate energy to the water, and it'll do that until the temperature of the block equals the temperature of the water. So these two are going to be equal. I don't know this value, and in fact that's what I want to figure out. This stuff here is mimicking a Q equals mass times change in temperature times specific heat. Okay, and if I know all of the almost all except one variable, then I can solve for the missing variable. Okay, so all right, let's see. My temperature of my water is looking like it is 19 degrees. Okay, so I can use Celsius here as long as I subtract them. So the temperature of the water is 19 degrees Celsius. You see the block boiling there. It's been boiling there for a while. Really shouldn't take too long for that block to become pretty hot all the way through the core. So let's take a quick moment and let's go ahead and pull that block out of there, and let's drop it into the water and watch for the change in temperature. Alright, I'm going to pull the thermometer out here just momentarily, and then I'm going to grab this block and drop it into here. Okay, so now the block is radiating energy to the water, and the water is going to start changing temperature. It's not going to take very long for the water and the block to come to an equilibrium point. The water was at 18 degrees, and now looks like we're slowly inching up. Looks like we're going to top out right about 24 degrees. Alright, so 24 degrees. I'm in Celsius here, so I'm going to subtract these guys off to make sure they're in the change in temperature, which can be in Celsius or Kelvin. Change in temperature in this case is 5 degrees. And this guy also is 24 degrees. Now notice how much these two things have changed. This one changed 5, looks like this one changed about 76 degrees. That in a nutshell is what specific heat really is. Now again, I have much more mass here, so that's not perfect, but let's take a moment and solve out for we want to find specific heat. So I can't solve for specific heat here because I don't have Q, but these Q's also are equal. In fact, this Q here is the water is gaining energy, so it's positive. The block is actually losing energy. It's getting colder, so it's losing negative, and it's a negative 76. So those negatives cancel. Let's take a moment, plug in the energy. Now, sometimes I do a known unknown table. It works sometimes it doesn't. The known is for the block, and the unknown is for the water. Now, what's unknown about it is the specific heat. So specific heat, temperature initial, temperature final, and specific heat, and Q, mass, and Q. Now I'm not going to go through this whole thing right now because it just takes too long. It's just the math thing. So sometimes I do set that up. But let's do the math here. So it's going to be mass of the block is of the water. We'll do the water first. 100 times the change in temperature, which is 5, times 4.18. Alright, and let's grab a calculator. What is our answer here? So it's going to be 100 times 4.18 times 5 equals 2,090 joules of energy. So this is 2,090 joules of energy. This also is 2,090 joules of energy. Is that actually perfect? We lost energy in lots of places, so that's a bit of a estimation there. Now let's solve out for the specific heat. So Q, which is 2,090, now again you could put a negative on here, equals a negative 7-degree temperature change times 121 times 4.18. Or it's not 4.8, that's what I'm looking for. Let's back that up a second. Alright, 70 times the mass, which is 121, let's multiply, not negative, times specific heat. So divide by 70, divide by 121 equals 0.24, 0.24 joules per gram degrees Celsius. Alright, so that's our first demonstration. Let's go ahead and look back at our first page here and just see kind of some problems here and see what we can come up with some answers on. Alright, so the first one says we got, and the rest of this should be pretty straightforward. You should be pausing it and trying it on your own. I have a 100-gram copper block heated from 25 to 50. How much energy is required? Okay, so you have a table or look this up. This guy has 0.36 joules per gram degrees Celsius. All of these problems are just going to be looking at this formula for Q equals mass times specific heat times temperature change. And if you ever wonder about the units on these things, they're on the specific heat. So joules, this is in joules, this is in grams, this is in Celsius or Kelvin. Alright, so let's do this here. So 0.36 times 100 times, we got to change it, 25. 25. Let's make sure we stay away from our picture. Alright. Alright, so, and I will go ahead and I will run this thing through. So I did TF minus TI. So it's gaining energy. Run through the math in here. 0.36 times 100 times 25, and I'm getting 900 joules of energy. 900 joules of energy. Next one, using energy from number 100 gram block of aluminum. Okay, so of course you got to realize that this is 0.9 joules per gram degrees Celsius. So Q equals mass times change in temperature times specific heat. Q is still going to be 900 equals the mass, which is 100 still, using the same mass. Change in temperature is what we're looking for, and the specific heat is 0.9. Now, in that case, you should be making some estimations about what you think this should be, alright? Because it's got almost a specific heat that's almost 3 times that of copper. So 900 divided by 100 divided by 0.9 is 10. Alright, so let's see what we got here. Okay, so it's 10 degrees. 10 was exactly degrees Celsius. Okay, so this one only changed 10 degrees, whereas this one changed 25. Same mass, only difference here is specific heat. This one changed almost 3 times as much because its specific heat is almost 1/3 less. End up different temperatures, specific heat. Alright, and then number 4, alright, let's try this problem here. We have a block of the mass of 50, and its 100 degrees Celsius dropped into 150 gram water, 21 degrees Celsius. If the water is warm to 23, what is the specific heat of the block? What's the identity of the block? So this is the lab thing we just did. And in this case, once again, we just start solving for the mass of the energy the water collected. So the mass of the block is 50, 100, drop 100 grams of water. So it would be the Q of the water is equal to 150, which is the mass of the water, which is right here. And then times temperature change, which is 2 degrees. Times the specific heat of water is 4.18, and let's go ahead and calculate that. It's 150, so 150 times 2 times 4.18 equals 1254 equals 1254, and that's going to be in joules, and that is the amount of energy that the block lost. 1254 equals, okay, and then looking for specific heat, the block started at 100, went down to 23, so 100 minus 23 equals 77. Alright, and then times the mass of the block, which is only 50 grams. Alright, and then I'm going to start dividing out here. 1254 divided by 77 divided by 50 equals 0.32. Specific equals 0.32. And the way you get the identity of this block is to look on your specific heat chart, maybe in your workbook or online, and try and match this value to a specific heat. And again, that's only an estimation at that point. Okay, so let's go ahead and look to the next page. Okay, so dissolving NaOH in water. Okay, now unlike dropping a piece of metal into water, we're now going to run a chemical reaction. How much energy taken in or given off will also depend on how much NaOH we dissolve. So we're going to run a little experiment here. Okay, and we don't need this anymore, but I'm just going to use a plain old beaker. You should be able to see that beaker, hopefully. And we're going to put a thermometer in there to get our initial temperature. Okay, so with this experiment, we have a beaker, and we are going to be dropping in some NaOH. Now I've already measured the NaOH, and it's at 4.4 grams. The water is 100 grams, or 100 milliliters. So once again, the water is my known collector. Okay. The difference is once the chemicals drop in, they dissolve, and the dissolving process allows these chemicals to release energy and warm the water up. So Q equals mass times change in temperature times specific heat. Now, unlike the block and the water didn't like commingle and create a new solution. This is actually creating a new solution, which could have a varied specific heat. But in all cases, because of where we're at in our school and in society, I guess just every resource possible, there will be a little star on here, asterisk, saying, okay, we're going to assume that this is just still pretty close to water. Okay. Now, in honors chemistry at high school, we may not mention that, but if you're running like an advanced placement test or something like that, they would just say, hey, by the way, just so you know, we're going to assume that this heat doesn't change that much. Okay. My mass is going to be 104 grams because that's the mass of everything in there. You can get 0.4 there if you want. And I'm looking for I'm actually going to record down this guy here. And this is going to be my change in temperature. So mass of the water is 1 water and everything is 104. Temperature initial of the water, let's grab this guy. And it is now sitting right around 19 degrees. Okay, 19. Now you see my table here. This is typically my known unknown table. We don't need a lot of it. Okay, all I really want is my energy. And let's go ahead and drop some of this stuff in here. So this is my 4.4 grams. I'll drop it in. And hopefully you can see okay here. On this little boat here, I'm going to pour a little water here in this boat, and then it will allow it to just kind of rinse it back in here. I'll keep doing that till I get all the NaOH in here. There we go. One more should do it. There we go. Okay, so I got 4.4 grams of NaOH in there, and it's going to take a few moments for this thing to dissolve. And it'd be nice if I had an insulated cup because I'm losing energy there. You know, good enough. Okay, so we'll take a few moments here and note that the mass of the NaOH here, I'll put this guy in it, 4.4 grams. Okay. All right, is there anything else we can do while we wait for this to dissolve? Let's see what we got here. Temperature here initially jumping up to just over 22, so we're going up. Okay. If we dissolve twice as much of the NaOH, we will get twice as much energy. This type of reaction is called proportional. Now you might call it linear. Okay, there's a few different terms for it. Write out the dissolving equation for NaOH. NaOH yields Na plus OH negative. Record the experimental data above. We did that. We started with that. We got to give ourselves some room so we don't get caught behind that video. Alright, there we go. And did that. Based upon the initial data, is the reaction system gaining energy or losing energy? Well, if the system is the water, it's getting hotter, so the system must be gaining energy. Which substance is doing the collecting of energy? That'd be the water. Okay. And technically it's the water and NaOH mixture because they're together now, but we'll just say the water. That's kind of how we generally look at it. Right now my temperature, we're about halfway dissolved, maybe a little bit less. We're at about 24 degrees, so we're moving up a little bit. How much energy did the water collect? Okay. So let's go ahead and start getting back to our math here and see if we can get some numbers. I need to get this final temperature here. And let's see, let's speed it up a little bit. Alright. Takes a moment or two. You could speed up the dissolving if you had a crushed NaOH. And we're getting awfully close, and I'm going to say we're going to end up pretty close to about 30 degrees. Okay, so at this point we'll go 30 degrees right here. So our change in temperature was 21 degrees. So let's go ahead and solve that out. It wants us to do that right over here. Okay, how much energy did the water collect? Well, the mass was 104, and then the specific heat is, we're saying it's not changing much from 4.18, and then the change in temperature was 21. Okay, and grab your calculator, and we got 104 times 4.18 times 21 is 9,129 joules of energy. Okay. Alright, so next question says, since we did not actually dissolve 1 mole of NaOH, what would be the energy if we dissolved 1 mole? Okay, so it says, remember enthalpy, which is delta H, is the amount of energy in Q per mole of the reaction as the reaction cycles through, one time through the process. So, and this is our reaction, so we're putting 1 mole through this thing. That would be the delta H on this guy. I didn't put 1 mole through, I put 4.4 grams through. 1 mole is actually 40 grams. If you add up the molecular weight of this thing, you're going to get 40 grams. That's how much the molar mass is of NaOH. So we need to do a proportion of this thing. So you could say something like 4.4 grams gave me 9,129 joules of energy. So you could use a proportion on this. 9,129 grams. What would 40 grams give me? This is just one way to do this, okay? Cross, multiply, and divide. You could just use a straight proportion to say, okay, what would it be if it were 40? Let's do that. Some people like just doing the proportion. It's 40 grams. All right, 40 times 9,125 divided by 4.4 equals much more, obviously. We're going to have 82,954. Now that would be, in this case, the number of joules per 40 grams, which is equivalent to the amount of joules, because that's 1 mole, per mole. So that's also going to be 80, I'm going to go in kilojoules, 82.9, so I moved over 3 spots, 1, 2, 3, 8.9 kilojoules per mole, per 1 mole. So that's just one way of doing a proportion. In some sense, you could just use factor label as well. What's the enthalpy change for this process? Well, it's just 82.9, because that's how much it is for that process to get kicked through one time. Alright, and our last question here would be, okay, we know that if delta H is the amount of energy it takes to push 1 through the cycle one time. So 1 mole, alright, in this case, gave us 82.9. But what if we put 2 moles through? That's what this is saying. I want to put 2 moles through. So this one would just be double that. And we got about 165.9 kilojoules. So really, the delta H for a reaction is very much determined by how you balance it. No difference here. So really, it's 1 mole per 82.9, 2 moles per 165.9. This is the same fraction. All right, hopefully this is helpful for you. Thank you.